just to recall to you what we said yesterday, we're looking at collisions right at the middle of these detectors. And as Chris said, here are a couple of people who don't normally stand on the beam pipe when the beam's in it, but to show how big it is. And what we're looking at is right in the middle of this collision, the conditions which we think existed at the early universe. So I talked about how we make a machine to produce the particles to make these collisions. And now I'm going to talk about how to detect events in these collisions, how to detect collisions that occur. That is, talk about these big detectors. And I'm going to talk about how to analyze the events that occur when we get these collisions. And then how, you remember that yesterday I tried to introduce the standard model and say what it was and what it wasn't. And now I'm going to start to talk about how well we test the standard model at the LHC, and just a first glimpse of trying to look after the standard model. So that's what we're going to do today. So let's start. Here is the machine. Here is the Alps, that's Mont Blanc, and we're 100 meters underground, and at various places there are big shafts coming underneath. And here is the Atlas experiment, and here is the CMS experiment. And I'm mostly going to talk about the Atlas experiment, but the CMS experiment is just as good. Well, I think Atlas is better, but the people on CMS think CMS is better, and they're competitors. They're nice competitors, but in this kind of enterprise, you need two experiments to be able to check each other. Now, that's another view, and I want to just recall the status that we talked about yesterday. Yesterday, we said that we had collected, during 2010, 48 inverse picobarns. Now, I explained what picobarns were yesterday, and I'm not going to explain it again. It doesn't matter. It's all relative. Suppose that is 1. Then, in 2011, we've already collected 25 times as much as we did in 2010. And we hope that by the end of the year, we'll at least double that. Maybe a bit more. So let's hope we get to 3 inverse femtobarns. And then in 2012, we're going to try to collect somewhere between 5 and 10 inverse femtobarns. So we've got a whole lot more data that is going to come in 2011 and 2012 compared with what we have now. But we already have a whole lot more that we're analyzing compared with what we got in 2010. So my first topic today is what are these two big detectors and how do we detect events in the two detectors. So that's what we'll do. First of all, the big detector called Atlas is shown here. Look how big it is. 25 meters in diameter and 26 meters in that central part there, and 44 meters total length. So it's a huge detector. It's the biggest microscope, I think, that's ever been built. So that's what the Atlas detector is, and here you see 2 people on it. There are something like 10 to the 8, that is 100 million electronic channels. That's a whole lot of detector to read out. We're going to talk about how to read that out in a minute. And it's got 3,000 kilometers of cables. So it's not something trivial. It took us a long time to build it. Here you see a guy standing in the middle of the detector. That is that part here, in the internal part, during the assembly. And these big bars here are what we call toroidal magnets, so that you have a magnetic field going all around the detector to bend particles and to measure their momentum. These are superconducting magnets, so they operate at 4 degrees Kelvin, minus 269 degrees centigrade. This is the CMS detector. It is smaller, only 15 meters diameter and 22 meters length, but it's heavier because they use different techniques to measure their particles, but in principle it's the same. There are collisions coming into the middle and the particles are produced and go out, and all these detectors around the collision point detect what is produced. Here you see a picture of the CMS detector during assembly. Now, now the fun starts. This is what we detect. What happens is a proton comes in, and I told you a proton consisted of quarks and gluons sticking the quarks together in the proton, and one comes in this side and one comes in the other side. In fact, most of the time, two of the quarks don't exist or don't interact, or just interact very little. And only one quark or gluon of each side interact. Here we have two gluons interacting, and boy, what is produced? We get particles produced, quarks, we get gluons produced, and in fact, I told you that in a strong interaction, the gluons and quarks cannot stay isolated. They have to turn into what we call hadrons. That's what we said yesterday. And so we see this fragmentation into hadrons. Now, that is the size of the interaction region of, say, something like 10 to the minus 15 meters. And then we get these particles outside. So we are the Sherlock Holmes trying to measure all of these particles outside and to figure out what goes on inside. It's a bit like two watches banging together, the springs and wheels flying all over the place, and then it's a jigsaw puzzle to put that watch back together again, or two watches back together again. So that's what we try to do. So I'm going to show you how we do it. Now this, I hope I can show you how to do it. This is a small, it doesn't have the sound, but it's a small clip that we made. Here is the detector, and you can see the detector is made up of different parts. We're going to go towards the center, and on the bottom there is where the interaction occurs. Outside that, we have, first of all, what we call pixel detectors and silicon tracking detectors, a transition radiation detector, a solenoidal magnet to bend particles. We'll see this in a minute, huh? A calorimeter to measure energies, another calorimeter to measure energies, like a Russian doll. And then we have our muon spectrometer. Now we're going to see the particles come out. Let's try first an electron. There we go. It produces a track in the tracking detector, and then it produces energy in the electromagnetic calorimeter. So we can measure the momentum and the energy. That's a photon. It doesn't produce a track, but otherwise it gives the energy. Finally, a proton comes out. It gives a track, a little signal in the electromagnetic, but most of the time it gives an interaction in the Hadron calorimeter. And that is a neutron, no track. Finally, we have a muon that gives a track and small signals in each of the calorimeters, and then gives a signal in the muon calorimeter. That's how we detect particles, and then sometimes there's a neutrino that's produced, and we don't detect anything. We detect neutrinos, or what look like neutrinos, by what we do not see. Now we have the interaction coming in. That's the proton coming in. It produces the interaction, And then we're finished. Blackness. Now, that's a summary of what I tried to show you there. There is one thing that I haven't said, and I will come to that in just a minute. The inner tracking detector detects charged particles, and because there is a magnet here, it bends the charged particles and measures their momentum. If we don't have a charged particle, that part leaves no signal. Suppose we have an electron or a photon that produces an interaction in this electromagnetic calorimeter and produces an electronic signal which has a magnitude which is proportional to the energy that's deposited in this calorimeter. Protons and neutrons do the same thing, except in this large Hadron calorimeter, and that goes behind the electromagnetic calorimeter, and then muons produce a track here, a small signal in the electromagnetic and Hadron calorimeters, and then is bent to give an independent momentum measurement in the muon spectrometer. So that's how we separate all the different kinds of particles. The neutrinos are only, as I said, detected indirectly via missing energy. By missing energy, I told you that energy was conserved in a collision yesterday. And so if energy is not conserved, we interpret that as being due to something else. We'll come to that in a minute. So I'm going to tell you how one of the detector works, and all of the other detectors work in a similar kind of way. This is just like a Geiger counter. Here we have a wire inside a tube, and the tube is closed and filled with gas. Now a particle comes through that tube, and it hits the electrons of the atoms of the gas and ionizes them. So you can see this path, I've lost my thing, you see this path of ionization here as the particle tracks. There is a positive potential on this wire and a negative potential on the tube, which is metal. So there's a difference of potential. And these electrons drift through the gas towards the wire. Sometimes they hit other electrons and multiply. But you get a signal, whatever happens, on the wire, and that can be read out and treated by electronics. That's the principle of particle detection in a gaseous tube. And in fact, the tracking detector of Atlas has 400,000 of those gaseous tubes. So that's 400,000 of the 100 million signals. Inside that, there are silicon detectors that are solid-state detectors. But the principle is the same. I'll show you that in a second. Finally, at the extreme inside, right against the beam pipe, there are what are called pixel detectors. Pixel detectors will measure the ionization of a particle traversing it in a little block of typically 50 microns by 400 microns, that is 0.4 millimeters, and it will leave a signal which is read out. Like a CCD camera, except instead of being read out once every 2 seconds, it will be read out 40 million times every second. Okay? So that is how the tracking detector works. Now I'm going to show you just a few pictures of the tracking detector. Here you see a silicon detector, and here you see the electronics. And this is the full tracking detector of Atlas. You see inside here the pixel detector. Outside you see 4,000 modules of silicon each containing 2,000 channels, and then you see all the gaseous detectors. The silicon detector is exactly like a gaseous detector, except it's solid, and the ions go to little aluminium pieces on the top of the detector, each around about 50 micron separation. In fact, 80 micron separation in the case of Atlas. And this leaves for everyone an electronic signal which is read out and stored. So I'm going to show you here. I'll leave this for people to look at later. That shows a little piece of silicon attached to an electronic chip. And you can look at it later, and some lucky person's going to take it away with him. This, you're not going to take it away. This is one module of the Atlas detector. So I'm going to pass it around so that you don't have to listen to me anymore, and you can really look at this and pass it around. But please give it back later. It's the only one I've got. It's one of the detectors that was built and it didn't work quite as well as the others, so we made it into a demonstration. So here, this is the electromagnetic calorimeter. It consists of copper plates that are bent in a specific shape. It doesn't matter the detail. And between the copper plates is liquid argon. And the liquid argon serves as the ionizing material, like the gas. You have signals read out using copper strips, and on the copper plates, that is where the electrons or the photons interact to produce their signal. So the signal that comes out of here is proportional to the total energy of the electron or the photon. And this is another view of the liquid argon calorimeter. The Hadron calorimeter is very similar, except it produces light, which is then converted into an electronic signal using the photomultipliers. So that is the calorimetry. Finally, these are the muons. You can just see now how big the Atlas detector is. These are the toroids, and they're plated around with gaseous detectors, exactly like I told you for the tracker, just bigger. There are hundreds of thousands of these little tubes and plates, and they cover an area bigger than a football field. So these are the two end plates here, and you can see the people down at the bottom who assembled this. What a task that was. So this is another view of the toroid. And this is a very nice picture because lots of people had really smart ideas when they saw these pictures going around. And one opera producer in Valencia, he produced an opera, The Trojans, in Valencia, using the decor of the Atlas magnetic spectrometer. Now, I told you that there was one thing that we hadn't talked about, and that is groups of particles, collimated jets of hadrons. So, what happens here? Quarks cannot exist isolated. So, as they leave an interaction, there is an immense force which is created like a spring between the two. And the energy of potential energy between a quark and an antiquark, or two quarks, increases as they are pulled apart. When it gets to be greater than the mass of the pion, or of another particle, E equals mc squared. You can produce mass. You can produce a particle. So what happens as the parton leaves is, I don't see it anymore, here it is that they break apart and they produce a jet of pions and other particles, but mostly pions. And these, because of the speed of the parton, these are collimated in a specific direction. So we can directly measure gluons or quarks leaving an interaction by collimated particles. And we measure these in the calorimetry like this. You can see the tracks being produced in the calorimetry, in the tracking detector, in each direction. You can see a third jet going away here. But these two jets have a very large energy deposition in the calorimetry. That is phi, this is theta. You can see a parton leaving here, a quark or a jet leaving in this direction, another quark or a jet leaving in this direction, that's theta, and here is theta versus phi for all the elements of the calorimeter.
Those are the angles.
Yes. Theta is the polar angle, and phi is the azimuthal angle. And here I flatten it out into a space. I'm sorry it doesn't come out very well, but you can see an enormous deposition of energy in the calorimetry. And we know that these come from quarks or gluons. This, by the way, is one of the highest energy two-jet events ever recorded. 3.1 teravolt of energy or mass is recorded in that particular event. That's a lot. Now I come back to what you saw yesterday. I'm not going to describe again cross-section or luminosity. I told you yesterday that the luminosity has to be made as high as possible. The cross-section is the physical process that we can think of as a probability, and the number of particles per second is what we measure. So we have different processes. And in fact, the total cross-section for everything that is produced in these LHC collisions is this quantity, about 70 or 80 millibarns. And everything else is much rarer. We get these collisions all the time, but every so often there is another one, maybe a Higgs. This is the energy of the machine, this vertical line. This is the energy of the previous machine at Fermilab near Chicago. And this is the energy where we hope to be in 2 years' time. This is the collision energy. This is the relative probability of the different processes. Why do I show this again? I show it because we're looking at very rare processes, and what we have to do is find these rare processes out of the jungle of all the other processes. That's no easy task. We're looking for typically one event in 10 to the 10 events which occur in the machine. So how do we do this? Electronics and computing power. I told you that we had 100 million electronic channels in this detector, and CMS has a similar amount of channels in their detector. So this is how we do it. This is a very complicated plot. I'm not going to go into the details of this plot, but what I wanted to show you was that this was the detector, and on the detector there is a lot of electronics. In the first few microseconds, the calorimetry signal and the muon signal is read out into a special processor, which we call the first level trigger. So there are 40 million bunch crossings per second, and out of those 40 million, we look at the patterns in the calorimeter and the muon over a period of 1 or 2 microseconds, and we decide, do we like this event or not. This is before anything else happens. If we like it, because it looks like an interesting process, and we'll see what an interesting process might look like in a minute, then we will read out the data, an enormous amount of data, and it all goes up into computer farms. These are immense arrays of PCs, Dell. And they treat the data and they reconstruct all the event and they read the interesting events out. So we collect roughly 200 events per second on disk. And that is sent to a central storage area at CERN. So this is the CERN Computer Center. So we read out 200 events per second, and that corresponds to something like 350 megabyte per second. So it's about half a CD every second. If we have DVDs, then it would be 10 times more. But you can see that we don't use CDs and DVDs to store this data. Okay, so that is how we make this detector work. Now, after that, there are fast links going all around the world, including to Tasmania. Sorry, not to Tasmania. Why I said Tasmania, I don't know. I was thinking of home, maybe. To Sydney and Melbourne, because they're members of these collaborations. And they...
Say Tassie couldn't do it.
Tassie could do it, but here they also go to South America, they go to Russia, China, all over the place in very fast links. And physicists are in these different places and they receive the data and analyze the data for the physics. And this is what we're going to talk about most of the rest of the time. Typically in Atlas and CMS, there are 100,000 jobs submitted to analyze the data every day. So it's enormous. I'm going to now talk about the physics. I hope I've given you an idea of how sophisticated everything is for the detectors and how we detect these events. So now we're going to look at how to reconstruct interesting events and interpret the physics. I showed you before this watch flying apart. And what we observe are the pions, protons, photons, electrons. And then we interpret the physics in between. So we're going to talk about the W and Z boson production. And then we're going to look at some other known resonances. And then we're going to rediscover the top quark. And then we're going to make a summary. This is confirming the standard model at this new energy of the collision of the LHC. So let's just remind ourselves. We have the standard model. We have the quarks and leptons. Here are the quarks, here are the leptons. We have the gauge bosons, gamma, Z, W, gluons. And the gauge bosons have mass 0 except for the W and Z. The quarks are sensitive to strong interactions as well as to weak and electromagnetic interactions. The leptons are not sensitive to strong interactions. They're sensitive to weak interactions. And the charged leptons are sensitive to electromagnetic interactions. And the masses of the gauge bosons and the fermions are acquired, we think, or we postulate, using the Higgs mechanism, and this I discuss in the next section of the talk. And remember that I said yesterday that this is sort of tacked on to the standard model. This is what we look at first. Z boson production. So here, it's easiest to look for the decays of the Z to a pair of leptons. Leptons are easy to see because they're very distinctive in the detector. So we look at E plus E minus, mu plus mu minus, tau plus tau minus, and we don't see nu bar because it's impossible to see. Z0 we can also look as Q bar. But Q bar is very difficult to interpret because there are many other processes in particle physics which produce a Q and an antiquark, a quark and an antiquark. So we forget about this. We look at these. And here you see an example. This is an example of two muons being produced in an event at the Atlas detector. This is one of the actual events. It was a Z goes to mu mu, collected on the 10th of May, and one of the muons had a momentum transverse to the beam pipe of 45 GeV, and the other one 27 GeV. Now, then, using these two muons, we reconstruct the mass of the muon pair. Now, when we do this, this could also be an electron. And this would be, in that case, it would produce an energy in the electromagnetic calorimeter for one of the electrons and for the other of the electrons. But I show you the example. Oops. I wanted to show you just once again what happens when a W is produced. You've seen this yesterday, except it was for a quark antiquark being produced yesterday. Today I'm going to produce you a W. So like I said yesterday, we go many thousands of times around the French-Swiss border. We've done that. We're entering into the detector, and we produce a W event. We don't see the W, of course. That's the collision. Particles are produced. We see an energy deposition in the calorimetry, the green thing, and a track pointing to it. That must be an electron. Let's see what it says. Yep, I was right. It's an E+. And there was something missing in the other direction because we were conserving energy in the direction transverse to the beam pipe. And so that's how we identified this particular W, which, by the way, is a true event which is superimposed on this video. So what happens in practice? In practice, we have here for a parton, which can be a quark or a gluon, combining sorry, let me start again. In this particular case, we have a parton which can be, in this particular case, a quark and an antiquark, combining together to produce a W. And they come from the original components of the proton. Then most of the quark information goes undetected, but these two produce a W or a Z. If I look at what we called the Feynman diagram yesterday, we have a quark produced with a Z in this case and two leptons, or we can have a quark and a gluon interacting to produce a Z with an associated quark going away and two leptons. Remember that time goes in this direction for this case. Okay? So that is how we produce the Z. Now, when we get many of these interesting events, remember that we've seen two electrons or two muons, and we've dragged them out of the detector and stored them in a special place for the detector. And so when we get a lot of them, we reconstruct the masses of the pairs. This is the formula for reconstructing the mass of the pairs, the energy of each lepton, multiplied by 1 minus the cosine of the angle between them. This is simply kinematics to produce the quantity mass. And when we plot for each particle which is produced, the mass, we see a peak. This peak has a width which is determined mostly by the accuracy of the energy measurement that we're able to measure in the calorimetry or in the muons for the 2 leptons that are produced. It also has an intrinsic width that comes from the decay. Here you can see for the full data sample from 2010, the distribution of the Z, and you can see we made many Zs, 1400 at the peak, and that's for the muon pairs, and this is for the electron pairs. The electron pairs are harder to identify, and sometimes a jet will fake an electron. And so you can see here a background of fake quarks, or fake electrons which are produced by quark jets. Now, from this, if we know the number of events that have been produced, if we know the luminosity of the machine, if we know the efficiencies of the detectors, then we can evaluate the cross-section for this process. And that's what we measure here. This is the cross-section measured at a very low center of mass energy in the 1980s. This is the cross-section measured at Fermilab, and they were measured in proton-antiproton colliders. What we see here is the cross-section for W production, and here the cross-section for Z production. Z is much harder to produce than W. And the line between them is the best theoretical estimate at present using quantum chromodynamics and the standard model for what the cross-section should be. And you can see the agreement is outstanding. Now these are the measurements for Z production, W plus production, W minus production, and total W production. So this is the sum of these two. This is a log plot. And here you can see the comparison with the QCD and a standard model prediction here and here and here. And I think you would agree that this is quite astonishing precision. So we were very happy to get this result. And CMS have very similar results, as you can see, to Atlas. This measurement shown here is not using the full data sample because there are sufficient number of particles of events produced that we're able to measure the cross-section with a small data sample, and we adjust at this time presenting the cross-section with the final data sample from 2010. Now, the Z is not the only particle which is produced. This is from CMS, and they plot every electron-positron pair that is produced, or mu plus, mu minus pair which is produced. And you can see here's the Z here, and the Z was discovered in 1984, and here there's produced what we call the upsilon, and there are 3 different peaks there, and they were discovered in 1978, and they are pairs of B quarks and anti-B quarks which join together to produce particles called the upsilon. And then here in 1974, this is what we call the J psi, and here is another peak which is an excited J psi, called the psi prime, and they are pairs of charm quark with an anti-charm quark. And you can see that the CMS detector has rediscovered these peaks and has measured the cross-section of these peaks to be in agreement with what you expect from the standard model. So that is an amazing achievement. I'm not giving up on the standard model yet. I'm going to talk about the top quark. And the top quark was first detected with just 6 events at Fermilab in 1995. We've got a lot more now. But it's a very complicated process. And the lower we go in the cross-section, the more complicated the kind of particles, the kind of event configurations that we have to search for using that trigger that I described. So here we have a proton coming in and a proton coming in the other direction, and we produce a top quark and an anti-top quark. Then the top quark will decay via the weak interaction, and it will produce a W and a B quark. Then the W will itself decay to produce a lepton or a quark pair, and in the case of a lepton, missing energy because it's a neutrino. So we'll have here very complicated events. Leptons, missing energy from the neutrino, jets, 1, 2, 3, 4. Of course, sometimes this would produce a quark pair instead of a lepton and a neutrino. And that would be real trouble for us because we would have 6 jets and no lepton. And that we would find very difficult to distinguish from all of the other quark processes that occur with higher cross-sections. So we try to look for something with at least 1 lepton. Something else is interesting, and the B jet is produced, and all of these fragment into these jets in the calorimetry, but the B jet can be identified separately because they take a little while to decay. And so you can see them in this famous pixel detector that I showed you earlier. Typically, we have the tops, 1 lepton, at least 4 jets, and missing ET. And you will find that this is a typical signature that we're looking for with all the new physics we're going to look for as well. And in fact, the top, we want to know the top very precisely because it's going to be a background for the new physics. So if we only see half of the top and we don't understand the top cross-section, then we will pretend that what we see from the new physics is something that is really the standard model. So we have to be careful to make sure that we understand this very, very well. So how do we go? Let's do this. Oops. Here you see an event, and you can see how busy it is. My God, it's busy. First of all, we get many events in a given traversal of 2 bunches of protons, because the intensity is so high that you can get at present, on average, 8 events produced in every interaction. So the tracking detector has to pick up all of these vertices and to separate out the one that deals with the top quark. Then it has to look for a muon, and here, or an electron, and here you see a muon. Here you see a jet of particles produced in the tracking detector and a few millimeters with nothing. And that's characteristic of a zero charge B meson, which is produced. It's a B quark clothed as the Hadron, which decays after 10 to the minus 13 seconds, that is a few hundred microns, multiplied by the boost that comes from special relativity. It's called time dilation. And in practice, it's a few millimeters. And so you can reconstruct that jet using the pixel detector as an offset vertex. So this is a very important tool for identifying top events, because usually there are at least 2 B-jets. Then, once we get that, we make various kinematic distributions. This is the distribution of the mass reconstructed from the 3 highest energy jets. And here you can see what you expect from T-bar production. Here you can see the background of fate signals that we expect from WN jets, ZN jets, single tops, QCD, and so on. When we put all this together, we can measure the cross-section. And this shows you the most recent cross-section estimate using 180 inverse picobarns, so using part of the data. Sorry, my apologies. This is the value of the cross-section using the full 2010 data set. And here you can see the measurements at Fermilab where the top quark was discovered. It was very hard to discover it because the cross-section at Fermilab is much lower, 10, 20 times lower than at the LHC because of its energy. And here you can see the measurements of Atlas and CMS, and they agree incredibly well with the QCD expectation. These vertical lines give an indication of the precision of the measurement in each case, and the purple line, the purple bar here, gives a precision of the theoretical prediction. So you can see that everything fits extremely well together. Now, they are not the only things in the standard model that we measure. This shows you a summary of all the measurements of the 2010 data set for CMS, and the comparison, the ratio of the measurement with respect to theory for different processes. And you can see how well things work. The bigger the error bar, the rarer the process. So we believe that the standard model is very well understood at LHC. This shows you the same thing at Atlas, and you can see W and Z production. That is the cross-section. The probability of it occurring, that is here. Then we see W production associated with a photon, which I haven't spoken about. You can see the comparison of the measurement with the theory. Z with the theory, and that is much lower, so that will be here. Here you can see T-bar production, that is here. Here you can see single top production, which is very rare and very difficult. And finally, we're able, or we have measured, 2W production in proton-proton collisions and 2WZ production in proton-proton collisions. And they are not shown on this plot, but they will be roughly a factor of 10 less than the T-bar production. That's interesting because we're able to measure those processes. 2 electrons plus 2 neutrinos, or electron and a muon plus 2 neutrinos, an electron and neutrino plus 2 leptons. And we were able to measure that, and you can see that they would have a probability of occurring which is more or less the same as the Higgs boson. So that's what we want to go look for next. We are now going to start looking for the Higgs. We haven't found the Higgs, by the way, yet, but we hope we might. Just remind you from yesterday what it is. The Higgs is the simplest mechanism, is the simplest way of giving mass to the W and Z bosons. But it's not a unique way. So we're not convinced that we will find the Higgs. We're looking for it. And in fact, for the standard model, it's applied somewhat artificially. The mass of the Higgs is not predicted by the Higgs mechanism applied to the standard model. And so we don't know what mass it is, or we only know indirectly a range of possible masses. The couplings, though, are very well known in the model of the Higgs. The LEP, E plus E minus collider at CERN, excluded the existence of Higgs for any mass of a standard model Higgs for any mass less than 114 GeV. The Tevatron, the CDF and D0 experiments at Fermilab have so far excluded the Higgs in this region. We'll come to see what that means in a minute. These exclusions are with 95% confidence level. That is, we believe that we could be in error with these predictions only 5% of the time. Now, this is what we expect to happen for the production cross-section of the Higgs boson. I showed you just a few seconds ago what we might expect for the Higgs. This is the Higgs as a function of energy total for a mass of 120 GeV, the top one there. Now, what we do here, we separate it out into different processes. The most common process is for two gluons from each of the protons to join together to produce a Higgs. The second most common process are two quarks from the protons to produce W's or Z's, and then to produce a Higgs. We're not going to go into the details of these processes, but you can see that this is the cross-section for one of them, and this is the cross-section for the second most likely. As I said, we do not know the mass of the Higgs. We believe it should be less than 600 GeV, and in principle, if the standard model is correct, less than 180 GeV. We expect it to be light in the standard model. But we do not know. 10,000 events would have been produced in Atlas or CMS if the cross-section is that, and 100 would have been produced if it is that. But we only see a small fraction of what is produced for the following reason. This is a very complicated plot. Don't worry, I'm going to explain it. I said that the couplings of the Higgs were very well defined. In fact, the Higgs likes to grab hold of the heaviest object possible. So when it is kinematically possible to decay into a W and a Z, it will. The heaviest thing it can do to decay into at lesser mass is a B and B bar. So it is that which is dominant. That is almost impossible to see against a background of top bar events or QCD events and so on. So we're not going to talk about that. The easiest thing to see at low mass is the decay of a Higgs into two photons. And that, as a function of mass, shows you the fraction. So out of 10,000 Higgs produced, if it was a mass of 120, we would see 2 times 10 to the minus 3 of that, so we would see a maximum of 20. Maximum of 20. If it was of higher mass, we wouldn't look for the gamma-gamma because it would be impossible. Suppose it was 200, then we would look at the WW and the ZZ. Okay? So we're going to look at how we reconstruct these. We're in the process of doing it, and the first results will be presented at the conferences in a few weeks' time. What we would do in the case of gamma-gamma is search for two very energetic photons. Remember, detected by no track in the tracking detector, followed by the deposition in the electromagnetic calorimeter. And, in fact, that's what we do. Then we measure the angle between the two photons and the energy, and we measure the mass of the photon pair. Unfortunately, there are many, many other ways in which you can produce a photon pair via strong interaction processes and electromagnetic interaction processes. So, well, strong interaction followed by electromagnetic. So, in fact, this is what we simulate, we would expect from all the different processes in a data sample of 1 inverse pentabarn. This is a Monte Carlo simulation. And this is what we would expect, 10 times the signal that we would expect from a Higgs in the standard model at 120 GeV. This is the data that we have collected and made public so far. And similarly for CMS. You see 1/5 of this amount, and you can see the measured data in these black points as a function of the photon mass, and you can see the expectation of the background. And there is no significant signal so far. So this is work in progress. But you can see how we can measure the Higgs if it exists at a given mass, for example 120, we would see a peak, gradually coming up here as we accumulate more data. The other thing we look for is Higgs goes to WW. We're really anxious to find this particle if it exists. This would be a candidate for the Higgs goes to WW. We do see candidates. This is one particular event. Here you can see a muon. Here you can see an electron. Here you can see missing energy. So this is 1W decays into an electron plus missing energy, and the other decay is into a muon plus missing energy. This is a simulation of two Zs, one going through the muon and one hitting the electrons. I would have liked to have shown you a real event for ZZ production, but I'm sorry, it is so rare that we haven't seen it yet. But when it comes along, we will see something like this. Okay? Now, as I said, if I don't see something, we don't have a cross-section. So we can only put a limit. This is the limit that we have obtained so far using the 2010 data. This is the measured total cross-section of the Higgs, as I stated. And this is how well we can measure it. This is the upper limit of how well we can measure it so far with that data sample. So we need something like 10 times as much data to become sensitive. Now, we do have 10 times as much data now, and that is what we next have to do. I'm running out of time, so I'll be very quick now. So what we do now is to try to look at the extra data. And if we have 10 inverse pentabarns at 7 TeV by the end of 2012, we will be able, to a level of 1 part in a million, less than 1 part in a million, discover the Higgs between about 125 GeV. Here we have 5 pentabarn for each experiment, 10 pentabarn for 5 pentabarn for each experiment, 10 pentabarn total. We can have 5 sigma sensitivity between 117 GeV and 535 GeV. So we believe that if the standard model exists, we will discover it before the end of next year, if it exists. Now, we're also going to look beyond the standard model. This shows you the Z distribution. Now, you saw before the Z distribution with all those peaks, and I had a question mark. What happens, oops, sorry, what happens above the Z? This is the Z, and we have events from E plus E minus or mu plus mu minus up to nearly 1 TeV, 10 times as high. Some processes can be producing these lepton pairs, but there can be new physics. There can be more than one Z, or there can be particles that look like a resonance due to extra dimensions and so on. This shows you what we expect, and this shows you what would happen if we saw these new particles. So already, this shows you, by the way, one particular event with two electrons of 920 GeV mass, almost here. So this shows you for different models, extra dimensions, a new Z being produced, what the cross-section would be, and this shows you what we measure. So we have placed a limit so far on excluding any new Z prime, or also any new W prime, less than these values. So if they do exist, they will be very, very heavy. And this is the start of an investigation for the future. We do the same thing for the two jets. And from this, we can look for deviations of the expected two-jet behavior. And this is now, again, Rutherford's experiment, all over again. If Rutherford had composite quarks and they existed and they were with a size that was accessible here, we would see a deviation from this line. We see a couple of events, but that is very small statistics, and integrated above this value, there is no excess. So, we do not see composite things like Rutherford in our data so far. In fact, we have a measurement that if there are composite objects, then the composite limit should be more than 10 or 9.5 TeV. This places a size on the quark, and I told you yesterday that it was less than 10 to the minus 19. With this new measurement, it places a limit measured and expected of nearly just a little bit more than 10 to the minus 20 meters. So it's getting very small. I remind you that the electron radius is 10 to the minus 24 meters, and in fact, this is a good measurement, and it's now nearly much better than this because somebody asked me a question yesterday about spherical electrons. And so I checked it last night when I went home, and in fact, it is very bad the way they talked about it in the newspapers. A spherical electron talks about the sphericity of charge in the electron, the existence of a dipole moment. So it was a measurement of the electron dipole moment. And in fact, the measurement, in fact, placed a better limit on the size of the electron. That should be electron there, not your. It's on the size of the electron than what I show here. So that is what the measurement was. Very important, by the way. I have now run out of time, so I won't speak about Susie, except to say, we can do it later, except to say that we've already placed limits on Susie, which is significantly more than what existed in the previous accelerators. So I'm concluding now, and we can discuss Susie over lunch. It's a nice topic over lunch. And so I hope that my description of CMS and Atlas showed you how we use these detectors and how we identify the different particles that are produced in the detectors. and how we acquire the data in the detectors. Now, from that, I reconstructed, first of all, WZ production, and then top production. I reconstructed the two watches hanging together and creating particles. And I interpreted the physics. Now, what we're doing now is going beyond that, and we're looking beyond the standard model. First of all, for the Higgs production, and secondly, for hints of how the standard model should be extended at higher energies in order to remain consistent at very high energies. And this is for the future, so in 2 years' time, I hope we'll have a lot more to tell you about the course. Thanks very much.